Camden Thomas, and I'll be going over Lab 3 for Physics 2211. Introduction. Part 1's purpose was to calculate the mass of a black hole by annualizing the gravitational pull it has over a star in orbit. Part 2's purpose was to find the initial velocity of a ship launching off the moon to attempt to orbit both the moon and the planet without crashing. The principles used were Newton's second law that relates the net interactions between the system and surrounding motions, and Newton's universal law of gravitation, which shows the non-constant attractive forces between two or more objects with mass. These are some more of the equations here for the principles that we used during this lab. These are some of the equations we needed for our coding and to find the mass of the black hole. This is the system for both parts, where in the system we had the star and the black hole with zero surroundings, and in part 2 we had the ship, the moon, and the planet that the ship was orbiting. These are the initial coding conditions for part 1 with the star and the black hole. This is a screenshot of part 1's results with some of the calculated masses for the black hole. We got an average for the black hole's mass being this number, and then you can see the calculations for the net force and its individual components here as well. This lab helps to show how the net force of the parallel and perpendicular components differ from the rate of change of momentum's parallel and perpendicular components within the isolated system. The initial coding conditions for part 2's lab. Here you can see the initial velocity of the spaceship, where I equaled it out at both 24,300 meters per second in the x and y components, and our objective was to find an initial velocity of the spaceship that can orbit both the planet and the moon indefinitely without crashing. These are the results of inputting those as our initial velocity components. Though it does orbit both the moon and the planet, it unfortunately does not create a figure 8. Are some of the potential errors that could have occurred in both parts. In part 1, there was rounding of iterations throughout the simulated loops that could have possibly misrepresented reality. And in part 2, there was trial and error used to find the initial velocities, and a more appropriate formula or method could have been used for more concise calculations that would have gotten us closer to the desired figure 8. In our discussion, we can see that the net force of the spaceship is solely affected by the gravitational forces of the planet and the moon. The moon's gravitational force is affected by the planet and insignificantly by the spaceship, though it is present. The parallel component, or direction of the movement, has direct influence on the magnitude of the rate of change of momentum, and the perpendicular component only changes direction and has no effect on the magnitude, thus creating a curving motion in the system. What if we wanted to predict the motion of the entire system if we added a black hole in part 2? The black hole's gravitational pull would affect all objects in the system. If we assume the black hole is of a great distance away, the moon would still be most affected by the planet, and the ship by both the planet and the moon, and the entire system would orbit the black hole. The black hole could potentially destabilize the system's orbit as time progresses if it has a large impact on the system, either due to its distance or mass. To conclude our findings, in part 1, we were able to use the coding simulations to find a close approximation for the black hole being 1.046 e to the power of 36 kilograms. And in part 2, we were able to find an initial velocity for the spaceship to be able to orbit both the planet and the moon indefinitely at 24,300 meters per second in both the x and y components. Thank you for watching.